So we're going to talk about the effect of light getting affected when it's passing through one medium to another medium, and specifically talking about the total reflection when a light ray is traveling from a medium with a higher index to a medium with a lower index. So I'm going to make an example. So let's assume this is our um, like boundary of medium, and we have N1, and that is, let's say, glass. So this medium is glass, and then we have N2, which is air. Now the reason I call them N1 and N2 is because we are going to talk about if the light ray is actually originating and the incident ray is coming from the higher index medium. The higher index medium is N1. So higher index medium, so this is an incident ray. We also call this angle with respect to the normal line theta I. So the angle of incident theta I. We also have the angle of refraction. So when light is traveling through a medium with higher index to a medium with lower index, for example, in this situation, the angle of incident is going to increase. I mean, the angle of refraction. So it's going to basically maybe look like this, which means the angle here is going to change. Surprisingly, this is not called an angle of theta r or refraction rate, even though this is refracted way. This is called theta 2. And theta I is smaller than theta 2 because the angle of refraction is higher when a ray is traveling from a higher index to a lower index. Now, what happens in total reflection is that as you are increasing your theta I, okay, so I'm going to change another color, and I'm going to imagine another kind of ray, maybe coming from this direction. Again, still coming from glass, but from a different source. So the light is coming through the surface, and again, because it's going from glass to the lower index ray, it's going to, the angle is going to increase. So my new basically theta I belonging to the new ray is going to be this much, and the angle is going to also increase, so maybe something like this. A very small angle, and this is our new theta 2. And there's going to be a situation where when you have your basically incident ray in a very specific angle, maybe like somewhere here, and again your new theta would be this one. This is our new theta I, the bigger angle. Now, because it's slower, it's actually going to be right on the surface of. So the refracted ray is not going to exit the medium. It's not going to exit the glass, and this only happens when you're going from higher index. That's the key point. It only happens if you go from higher index to a lower index. It does not happen if you go the other way. If you go from lower to higher, you will never face this situation because your angle of refraction gets smaller. In this case, it gets bigger and bigger, and it gets to a point that your angle of theta I becomes that angle that doesn't actually allow the ray or the light to escape. So in that case, we call that angle the critical angle. So the definition is the smallest angle of incidence of which the light ray passing from one medium to another less refractive medium can be totally reflected from the boundary between the two. So basically, it means that's the angle, that's the starting point. That from that point on, all the rays, all the light rays, with angle higher than theta I, which we're going to call it now theta C, because that's our critical angle. So anything higher than critical angle will definitely have a situation that the ray is not going to be able to escape from the medium, and it will have a total reflection. So one example for it would be perhaps if we have a different color, let's say, let's pick orange, and let's say we have something higher than the angle of the total critical angle. So let's say this is the light ray. And if that happens, we're going to just basically face a total reflection. So the light ray not only is not going to be able to escape, but also suddenly starts following the rules of total reflection, or the reflection, which is theta I, which are theta I. Actually, I must. This is our new angle. So I'm not sure how we can show it. I'm going to try. So this is the new angle. And it's going to be, again, equal to theta, our new theta R. So this is our new theta I and new R. And it's going to be following the reflected. So it's not going to be able to escape. Again, the example of it is that now if you are let's say this is if instead of glass, like it's water, let's imagine, and someone is in the water and it's trying to send you signal from this point. If they're trying to send you a signal from this point and you are, let's say, somewhere here, the light coming from this direction is not going to be able to pass through the wave and it will have a total reflection. Therefore, you will not be able to see if someone is going to send you any light signals from that location. Okay, so that's the best example we can make out of the situation. Another practical example is the technology, the same technology that is being used in fiber optics. Simply, fiber optics is the same idea. So I'm going to briefly talk about it here. Fiber optics, by the way, is a kind of wiring system. So in a traditional wire, we usually have like a piece of plastic all around. So this is like the insulator, which like doesn't make people get electric shock if you touch the wire accidentally. And there's a piece of copper inside, like a very thin piece of copper. And electricity, data, everything passes through this copper. Copper is a very good material to transfer. It's a good conductor. So electricity, heat, electrons, movements, data, everything moves through it very quick and smoothly. Now, the fiber optics technology came and said, okay, let's design a different kind of wire because we want to even speed it up higher. So let's make a different kind of wire, which is made of glass. Now, surprisingly, this is not plastic or copper or a kind of metal. It's just pure glass. And when it's not like any kind of glass. It's a specific type of glass, which we're not talking about the type, but it looks like something between plastic and glass. Like if you ever face one, you can like kind of like see inside how it looks like. Looks like this. And what happens is we figure that if we could simply send a light ray. Now, in this case, is going to be, again, a specific type of light ray, which carries information, energy, depending on the use that you're making out of this optical fiber optics. Now, it's going to carry some sort of energy or data with the means of light ray, in a specific type. And because the light ray initially is inside the glass, like in the very beginning in the center, when they send this light ray inside the fiber, uh, they send it in a very specific angle. When every time it hits the boundary of the glass and it wants to get out of the glass, it faces the situation that the angle is larger than critical angle, or it's at least equal to the critical angle. And when that happens, a total reflection happens.
Mm-hmm.
So the light ray just like gets reflected, and then again it gets reflected. So the light just gets inside until there is either a destination. So, for example, this could be a computer or a data system that is receiving all these information, or if in some sort of an accident or anything, like you get a cut um, in the wire, and then obviously from that point the light is going to escape and get separated from that point, and it would not necessarily continue to go. Of course, some of it is going to be still able to continue, but some of it will be lost. Now, when that happens, now you're dealing with information, data, energy, moving with the speed of light. Now, we talked about this. This is a specific type of ray and light for a specific use of fiber optics, depending on why you're using it and where. Also, this is a very specific type of glass. It's almost like a plastic glass.
Mm-hmm.
It's very specific, made for this reason. But still, what we're dealing with here is light ray traveling through a higher index. So let's call this the higher index, going to trying to go to a lower index, and we were referring to index of refraction.
Mm-hmm.
And because that's happening, there's a chance that this could have reached a critical angle, and therefore it's going to have a total reflection. And if you design it that way purposely, then obviously it's going to work that way, and your data gets transferred from one point to another point with the speed of light this time. Now, the technology is fairly new and there's a lot to work with, but that suddenly increases the rate of transformation of information between one point to another point, and that is the jump that we were facing a few years back, maybe 5 years back, when initially the higher internet generation has have been introduced to the society, where I'm talking about the years that internet used to have a speed of 1 megabyte, 2 megabytes per second, 3 megabytes per second, and companies were starting to promote 10 megabytes per second.
Mm-hmm.
Suddenly, with fiber optics, we're facing with 1,000 to sometimes 10,000 megabytes per second, which is all because of this technology. So this is one of the practical uses of the total reflection that we were talking about here, and that explains the situation in the use and the technology that is being used in fiber optics, and how it's beneficial and more efficient in a long run compared to copper. Now, copper, I just want maybe add a couple more points about, is not the best material for conducting electricity, heat, and things like that. The best material is actually gold. And because gold is very expensive and we are not able to use gold in wires, it would cost a lot of money just to do like the whole wiring of your house with wires that are made of gold. So it's not very common to do that. But if you come to very small scales of wire, very, very tiny little wires, then maybe use of gold will actually be beneficial, because gold is the best conductor, especially when if it comes to very, very small wires. Now, where do we use very, very small wires? Inside cell phones, inside computers. And now, I don't know if you heard the news, but there was, I think, about 5 to 6 years ago, that there was a person going door to door and asking people if they want to get rid of their computers, their old computers, like from 10 years ago, 20 years ago, the kind of computers or laptops that you have at home that are too old that you don't even like want to turn on, but you haven't thrown it out. And if you have one, he would buy it from you, and then he would collect it and go home and take out all those like small, very, very small pieces of gold, and then eventually accumulate it and get to like a reasonable like size and weight to sell it. And of course, I can't recall based on what law this was not promoted to be continuing that way, because it was creating a lot of different kinds of challenges and problems. But the idea is that gold is the best material to use, and we use it in very expensive devices such as let's say phone or computer devices that you have to use in like good material in a very small amount. But the next best one, which is very cheaper compared to gold, is copper. And copper is not as like smooth and have the high ability to conduct electricity and energy through it as quickly and as good as gold, but it has a very high rate compared to other metals. And most importantly is it's cheap. And when it's cheap, that's just preferred from a lot of companies, and because of economical reasons, most of the time people choose that. Again, if you're making a fancy phone or fancy computer piece, then that's a different story, but usually copper is being used. But now, compared to copper, the light rays used, the technology in fiber optics, are a lot faster.